Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
In today's lecture, we will not talk anything about machine learning, almost nothing about machine learning. It is just a very introductory lecture for probability, and it might get embarrassingly simple. So please let me know if you find it to be very, very simple. And also, unlike Vishy, I'm not used to giving these classes and all. So please let me know if I'm going too fast, too slow. If you want to see some particular derivation in detail, just let me know. Okay, so let me start with again like high school probability. So let's take a random variable x. So random variable is basically an outcome of a random process, and let's assume that it's a discrete random variable, so it can take some values x1, x2 till xn. Okay, and now we can define a probability over this space. So let's say, so a valid probability distribution over this random variable will be something like this. Like it should be greater than or equal to 0 for all I, and then this probability should sum to 1. Okay. So these random variables are basically univariate random variables, that it's just a one single number. These are not that interesting in machine learning. More interesting ones are basically where you have joint probability distributions, or you have random variables over several over basically a vector space. So let's consider a joint random variable which can take values x1, y1, blah blah blah, xi, yj, and then maybe xn1, yn2, right? So here again we can define this joint probability distribution given by these numbers for all ij. They should be greater than or equal to 0, and then similarly summation ij. Okay, so again very simple stuff. So here you can define. So basically you can, if you just want to study one of the random variables, you just want to ignore the other one, what you can do is just marginalize that out. That is, you can just take sum over, let's say, all j's, and that will give you probability of x is equal to xi, and this is called marginal. Similarly, you can figure out probability of y is equal to yj, summation over I. Okay, very simple. So now, so there is one more interest. So this is sometimes also called sum rule. So there is one more interesting probability distribution called conditional probability distribution.
Hey Prateek, we are having an issue hearing the voice. If you could increase it a little bit.
Okay, so I'll try to speak louder. Okay, so now let's just look at conditional distributions. So let me come here. So probability of x is equal to xi given y is equal to yj. This is your conditional probability distribution given y, and we can write this as like using Bayes rule. This is given as probability of x is equal to xi, y is equal to yj divided by probability of y is equal to yj. This is your marginal, and now, so this is very interesting because what this says is that probability of x is equal to xi given y is equal to yj times probability of y is equal to yj is actually equal to probability of y is equal to yj given x is equal to xi times probability of x is equal to xi. Again, something happened. I cannot do much. So this is something called product rule. And this rule is extremely important for machine learning folks because in some sense this is sort of the foundation of learning, and I'll tell you how. So let me get rid of this. So let's say you are in a system where you are given, let's say, you observe some points x1, x2 till xn, and also observe, let's say, some other variable or predicted variable corresponding to those points, y1, y2 till yn. So these are, let's say, just your real number variables. So let's say that is, this is your x-axis, this is your y-axis. So you observe some points like this. Okay. And typically in machine learning, you want to understand the system. So what you want to do is, let's say you want to fit a simple curve to these set of points, which explain these points well. So for example, you can try to fit a simple line. So one sort of real world example can be that this x-axis represents, let's say, relevance of an ad for a keyword, and then your y-axis can be your systems or what the CTR that you observe for that ad for those set of keywords. And now what you want to do is you want to understand that your predicted relevance by the system, is it good or not, and that's why you want to see how this curve behaves. Okay. So these set of points can be thought of as coming from some underlying random distribution, which you don't have access to or you don't know that well. And this line can also be thought of as, now since it is it itself is a function of these points, so this is also a random variable. Okay. So now using this product rule, so let me set up some notation. So let me call our observed points or my data set as something like this, and let me represent this line by normal to the line w, and I'll assume that the line passes through origin so that you don't have to worry about the bias or intercept. Okay. So in that case, I can, using this product rule, I can write probability of w given my data set times probability of data set is equal to probability of data set given w times probability of w. Okay. So here I'm using a little bit of shortcut notation, that is, I'm not writing w is equal to some parameter vector. So that itself is a random variable, but I'm just writing it as a short form. Okay. That is, rather than writing probability of x is equal to xi, I'll just write probability of x. Is that fine? Okay. So now let's look at this term. So what this says is that now given your observed data set, you want to find a w. Okay. And you want to find a w who's this, so this is called posterior probability, and we want, naturally I want a w which explains my data very well. That's why I want to find a w whose probability is very large given these observed samples, these observed training samples. Okay. Or in other words, whose posterior is very high, right? Now if I want to maximize this posterior, this data set is fixed. This I have already observed. So we can sort of ignore this. This is just a normalization constant, right? And here there are two terms. This term is what is called prior. So this is sort of like a priori knowledge of the distribution of w that we have. So this is sort of our belief about this W. So maybe we have a belief that our system is very good. This line is at 45-degree angle. Or maybe we have belief that our system sort of under predicts CTR, and then this line is very has very small slope. Okay. And this is called likelihood. That is, given some W, what is the probability of generation of these training samples? How probable are those training samples? Okay, this is clear. So now when I want to maximize my posterior, I essentially want to maximize this product. Okay, but sometimes you don't have any prior knowledge of this W. So the question is, do you want to just put some, if you don't have any good knowledge of W, then do you want to put some probability distribution in on your hunch, or you just want to ignore it? And that is a big debate point in machine learning, and actually this comes from statistics, so a big debate in statistics, and this is what is basically classical frequentist versus Bayesian debate. So I'll tell you what the debate is. So basically frequentists will say or assume that W is not a random variable, W is fixed. That is, you can just ignore this probability of W thing. You just want to maximize your likelihood. Okay, and this is called maximum likelihood estimate. So your WML is argmax of this, and this is called maximum likelihood estimate. Okay. Bayesian people don't like it. They say that, see, we might have some prior belief about W, or otherwise also we know that in general in this domain, this is how my weight vectors or this parameter vector W should look like, and they will try to put in some prior information about it. And if you put that prior information, that is called a posterior maximization. So give me 1 second. So that will maximize this quantity, and this is called maximum a posteriori distribution. Okay. So this is clear. For maximum likelihood estimate, you totally ignore your prior on W. You just want to maximize the likelihood of observing this data point given W. That is, you want to find a W that maximizes this estimate. For maximum a posteriori, you want to maximize your likelihood multiplied by your prior. So you have to put a good prior so that you can do maximization. Number one, the maximization should give you good W, and another thing is that this maximization might not be possible, in real time or efficiently if you put some weird probability distribution on W. So you typically want to put good probability distributions that will give you fast maximization. Okay. So the whole machine learning basically tries to do just these two things, one of the two things. The main challenge is now how do you model these probability distributions? How do you model your parameter vectors? What class of parameter vectors you are looking at? And how do you model your prior? So those are all part of the challenges, but overall goal is just this much. You can take any learning algorithm or any reasonable learning algorithm and you can try to put it in one of the two frameworks. Okay. So Now that we have some idea of why we are learning these probability distributions, etc., let's just go back in basics of probability, probability theory. So let me define some very basic things. So one is expectation. So if x is a random variable, let's say fx is a function of this random variable, then expected value of fx is given by f of xi, probability of x is equal to xi, I goes from 1 to n, let's say support of x's and so on. Okay. Similarly, you can define variance of fx as expected value of fx square minus expected value of f of x square. Okay. And then one like very sort of nice thing about expectation is that expected value of fx plus some g of y is given by expected value of fx plus expected value of gy. This is called linearity of expectation, and this is also heavily used in several parts of learning. Okay. And then if you have some, let's say, two random variables x and y, you can define covariance between x and y as expected value of x, y minus expected value of x times expected value of y. And covariance essentially sort of indicates that how correlated x and y are. So that is, if you, let's say, increase value of y, then is value of x likely to increase or decrease? So if your covariance is positive, it is likely to increase. And the strength is more and more if your covariance is 1 or minus 1. At 0, essentially they are essentially independent. That is, if covariance of x comma y is equal to 0, that implies that x is independent of y. That is, outcome of y has no bearing on x and vice versa. That is, if let's say if you toss two coins, then whether first coin gets head or tail doesn't matter at all to the second coin. That clear? So this is the symbol for independence. And in terms of conditional probability distribution, basically independence says that probability of x given y is probability of x only. Outcome of process y has no bearing on outcome of x. The probability distribution remains exactly the same. Okay, so now that we have defined these basic things, let me just so far I've just talked about these discrete random variables. We can define exactly the same things for continuous random variables. There we will not have this probability distribution function, but we'll have probability density function. And what that essentially says is that, so if this is my probability space, this is my x space, and this represents my probability density curve, then probability that, so this region indicates probability of random variable x lying between some value x plus delta x to x minus delta x, and that is essentially given by this probability density function, which I am writing by small p of x times 2 delta x. Okay. And that's why you can define all these quantities analogously. So you can, rather than this, you can define it to be minus infinity to infinity fx times px dx. Okay. That okay. All right. So now that we have defined some very, very basics of probability theory, let's just consider few probability distributions which are very, very useful in learning in general. And I'm sure you must have you must know quite a bit about most of this distribution, but we'll just refresh some of those. So let me get rid of this. So first is your extremely simple Bernoulli distribution. So basically this is a discrete distribution where x can take two values, 0 and 1. 0 can, you can think of as representing tails, 1 as heads, and now probability of x is equal to 1 I define as mu. That's why probability of x is equal to 0 is 1 minus mu. And essentially you can write this probability distribution as something like this. X is equal to x as mu to power x, 1 minus mu to power 1 minus x. Right? And then some very simple statistics about these things. So expected value of is mu, variance of this random variable is given by mu 1 minus mu. Okay. And now let's go back to our frequentist thing. That is, let's say I observe small number of these random variables. Let's say n of them. That is, I have one single coin. I toss it n times and I observe whether I got head or tail. If I get head, I will say 1. If I get tail, I will say 0. Okay, this is what xi will represent. Xi is on ith trial whether I got head or tail. Okay, and now so I have no idea how biased the coin is, whether the coin is totally unbiased, whether it is biased. I have no idea. I just want to figure that out. Okay, and for that I can say that okay, I can write the problem as I want to figure out my mu, which I don't know, given this data set, right? So for figuring this out, I can take, let's say, frequentist approach. That is, I'll just maximize my likelihood, which will imply that, so my mu ml is given by maximize or argmax. My mu actually should be between 1 to 0. And then I just want to maximize probability of these observations given mu, right? That's fine. Now all of these observations I have said that they are independent of each other. That is, one trial has no bearing at all on the next trial, right? So that's why using independence I can write this as argmax multiplication over each trial, probability of xi given mu. This is fine. And we have explicit representation for this distribution. So mu to power xi 1 minus mu to the power 1 minus xi. Okay. So this is essentially just mu to power summation xi 1 minus mu to power n minus summation xi. I want to maximize it. And you can clearly, basically you can take log of this. Log is a monotonic function. So even if you take log and you try to maximize the resulting expression, the maximizer will be exactly the same, right? So I can just take log, take differentiation, set my derivative to be 0, and what you'll see is that this mu ml comes out to be summation of xi by n. That is the maximum likelihood estimate for my mu, which is essentially like probability of me getting head, is given by summation xi. I goes from 1 to n by n. That is, I'll just measure on an average how many heads I've got, and that will be my probability of getting head. Okay. So here, one big criticism of this approach is that if my n is, let's say, very small, 5, 7, then this estimate is not at all reliable. I mean, there was a time when Dhoni lost 8 consecutive tosses. So does that imply that that coin was biased? No. So just, it can happen easily. So if you have such a small sample size, these maximum likelihood estimates can actually be very poor. And that's where basically Bayesian people will say that don't do this. Let's try to bring in our prior knowledge also to make these estimates more robust. So as I said earlier, that the prior that you put, you can put any prior. I mean, it depends on your belief, but one of the goal should be that it should be able to, like you should be able to maximize your, like compute this maximum likelihood or maximum a posterior solution easily, number one. Another thing is that it should have at least some good interpretation for that particular problem or domain. That why did I select that prior? So for this particular problem, the prior is a popular distribution called beta distribution. So beta distribution you can essentially think of as a distribution over mu. So it's given by, and it is dependent on 2 more parameters, and these so mu itself is a parameter for us. So we call these parameters of beta distribution as typically hyperparameters. Okay. And this is given by this gamma function of, I think, a plus b by gamma of a b times mu to the power a minus 1 and then 1 minus mu to the power b minus 1. Let me see if let me define gamma function properly. I don't remember it ever. And this gamma function is given by, so gamma of e is given by minus infinity to infinity. So it is some function. I'm pretty sure most of you know that if a is an integer, then it is given by a minus 1 factorial. If a is integer. Okay. So one very nice thing about, like you can clearly observe that why beta distribution is used in conjunction with Bernoulli distribution, because the form is very much similar. You have mu to the power x, 1 minus mu to the power 1 minus x. You have very similar form here. And like here we are just observing it by, like just visually we are observing it, but there is much more deeper connections between these, and for every distribution you can define this sort of conjugate distribution, using which, for which you have very nice properties for your map estimation. And that is called conjugate prior or conjugate distribution. So for your Bernoulli distribution, beta distribution is your conjugate prior. Okay. So now let's look at our map solution. So can I remove this? So your map solution, as I said earlier, is given by argmax mu between 1 to 0, probability of data set given mu times probability of mu. given these hyperparameters, which we assume to be given or fixed. These are essentially your sort of belief about the system. So as we did earlier, using independence of these xi's, you can write this as argmax mu to the power summation xi 1 minus mu to the power n minus summation xi. This is what this gives, and then this will give us mu to the power a minus 1 minus mu to the power b minus 1, right? We ignore this normalization constant because this is just dependent on a and b. It doesn't depend on mu at all, so we just ignore that. And again, when you try to maximize this, you can just take log of this function, set the derivative to be 0, and interestingly, your mu of map will come out to be something like summation xi plus a minus 1 by n plus a plus b minus 2. Okay. So this prior has very interesting, like you can explain this prior very well intuitively. So what essentially this says is that I will do a plus b minus 2 pseudo trials. That is, these are not trials that are given here. I will just assume that I have done them. And I also assume that I got a minus 1 heads. Okay. So this is just to make your estimate more robust. That even though you might see just five trials, rather than giving wildly bad probabilities, you can just use this to use some at least somewhat reasonable probability distributions or estimate of mu. Okay. So this is clear. Should we move on?
So you have to fix A and B.
Yeah, so A and B now needs to be fixed, and that has to be fixed upon some prior knowledge or some belief, or typically if you don't have any knowledge, you will just set A and B to be 1 each, 2 each, so that you are saying that I did 2 trials, in one of them I got head, in one of them I got tail. Because I don't have any information, I'll just put that. And that will essentially, what it will do is it will regularize your solution towards half. That is, you will say that in practice or in real life, I've seen that coins are not too biased. So I'll tend my coin to be, try to keep it unbiased. Okay. So that is another nice thing, that is, so these priors have a nice interpretation as regularizers of your solution. That is, it will not let your solution, like your map solution, to fly all over the space. It will tend to keep it towards some sane quantity. Okay. So this is clear. Should we move on?
So one question.
Yeah.
In the Bernoulli distribution,
Mm-hmm.
what is the probability? What is that random variable that is requiring?
So this random variable x can take 2 values. Oh, you are still here. Okay, there is a lag. Sorry. So x can take 2 values, 0 and 1.
Yeah, that I understand. So what is the probability of x equal to x? What is that?
Probability of x. Oh, sorry. So these are basically different trials of your Bernoulli distribution. That is, what you'll, let's say you have a coin and just do toss. And if you observe head, you will say that, let's say your ith outcome xi is 1. If it is tail, you will say it's 0. So there is some confusion, as in I have used x is equal to xi here, and then xi here is outcome. So so that is different.
What is the first xi mean?
Which xi? First.
PR equals PR xi, x equal to xi. What is that?
Oh, so this essentially means that probability of x is equal to 1. So, or probability of x is equal to 0. So this x can take 2 values, 0 or 1. right? So here basically if you put x is equal to 1, you will see mu to the power 1, that is mu, and this is 1 minus mu to the power 1 minus 1, that is 0. So this term goes away, so it's just mu. So this is just a way of representing this thing compactly. That's pretty much it. Okay, so let's move on. Let's look at slightly more complicated distribution, which again most of you have heard of, which is binomial distribution. So binomial distribution can be thought of as if you do, let's say, k trials of Bernoulli, or let's say n trials of your Bernoulli random variable, then how many of them got heads? You can define a probability distribution over that as well. And this is essentially what binomial distribution will do. So it takes value from 0, 1 till let's say n. And then again, very easily, probability of x is equal to, let's say, some m is given by n choose m. Your mu to the power m, 1 minus mu to the power n minus m. Okay. So this is fairly simple. Basically, if you want to say that, okay, I got m heads, I'll figure out first in how many ways I can get m heads, and then write probability distribution corresponding to it. Okay. So essentially this x can be also thought of as summation xi, I goes from 1 to n, and each xi is a Bernoulli random variable. And just as a refresher, n times mu, and then variance of x is n times mu 1 minus mu. Okay. All right, so let's move on to more interesting distribution, which is multinomial distribution. And this distribution is, along with Gaussian distribution, this is one of the most important distribution in learning literature. So let's say if you have text documents, most of the time you use multinomial distributions to model them, to model uncertainty over text documents, because your text documents are typically represented by these TF-IDF vectors, which are essentially positive vectors, and this distribution is over positive quantities, or it's a positive distribution. So that's why it's extremely powerful and extremely useful, especially for text data, which number one has this property that it is like all the elements are positive, and second it is sparse, and it is useful for both of them. Okay. So this is just a multinomial is just a sort of extension of your binomial distribution. Okay. So in binomial distribution, what happens is you can observe only two outcomes, that is you get heads or tails. But rather than that, suppose you are rolling a dice and you can observe six outcomes, right? Number 1, 2, 3, 4, 5, 6. So multinomial essentially helps generalize binomial and Bernoulli distributions to those settings. Okay. So let's look at first generalization of your Bernoulli random variable. So in Bernoulli random variable, your x could take just 0 and 1. Now here in multinomial, your x can take, let's say, k outcomes. K outcomes. And the way we represent it is using a vector, okay, which has n bits, or sorry, k bits. Okay, that is, let's say, let's consider the example of dice. So if we observe, let's say, 2 on our dice, so we'll say that we observed 2 and remaining everything was 0. So this is 3, 3, 6. Okay. Okay. So this extension is clear. Okay. So now let's define the probability distribution. So is equal to x. Now here x is a k-dimensional vector, and that is given by mu k to the power xk 1 minus just this. Okay. So what this essentially says is that for each of your dimension, you have your you have a parameter associated mu1, mu2, which essentially says that okay, what is the probability that you get 0 here? Oh, sorry, 1 here. That is mu1. What is the probability that for the second bit you get 1? Okay. And you have this property that summation xk should be 1. That is, you'll observe at least some outcome. Okay. And similarly, summation mu k is equal to 1. Xk is positive, like it's between 0 to 1, and similarly mu k is also. Okay. So these sets are also very important or interesting. These sets are what's called simplices. So it's a k simplex. Similarly, this is also a k simplex. Okay. So now let's look at the multinomial, so this is just a generalization of your Bernoulli random variable to k outcomes. Now we can similarly generalize your binomial distribution to multinomial distribution, where you can have n outcomes and you observe how many times each outcome occurred. That is, let's say if you have a dice, you rolled it n times, how many times you observed 1, how many times you observed 2, and so on. Okay. So multinomial, again, like the same thing, it's over this vector. Now here, rather than just being the outcomes, these vectors are essentially the counts, that how many times you got 1, how many times you got 2, and so on. And then your distribution is given by so you will have first n choose, so n factorial by m1 factorial, or I'm sorry, what do you have to do? Oh, sorry, 1 factorial, and so on, times 1 to k, and then I to the power mi. So let me explain this. Actually, this I have to write a vector m. This vector m is of the essentially all the counts m1, m2 till mk. So mi represents the number of times you observed ith outcome. Okay. And then this will be your distribution. We know that summation mi is equal to n. That is, in total you observed n outcomes. Oh, and I have to put this n minus 1. And then mu I represents, your outcome being 1 for ith outcome. That is your ith outcome being present. Yeah. Okay, I'm sorry. So this is n factorial by m1 factorial, m2 factorial till mk factorial. Pi I is equal to 1 goes to k mu I to the power mi 1 minus mu I to the power n. Right. I'm sorry. I didn't get you. Because on the remaining you don't want that ith out.
occurrences.
Yeah, actually, sorry. Here you don't need. Yeah, here you have this extra constraint, right? That summation mi is equal to n. Yeah, I was just generalizing binomial, and that's why I made the mistake. Sorry. So you can see that for binomial, basically you'll have two terms. One is mu to power m, and then second term will be, so mu2 will be 1 minus mu, and then similarly m2 will be n minus m. Okay. All right. So interesting thing is that if you do your maximum likelihood estimate over this distribution, we can show it to be summation xk by n. That is, if you want to figure out your bias of your kth coin, that is, what is the probability of getting outcome k, you can just obtain it by summing, basically just counting how many times I got 1 divided by total number of outcomes. Okay. And now, so this is just your maximum likelihood estimate. Similar to your Bernoulli random variable, if you want to go to maximum a posteriori estimate, here again there is a very nice conjugate prior is defined, and that is called Dirichlet prior. So this Dirichlet distribution is over these mu i's. So you have k of the mu i's, right? So this distribution is over these k mu i's, or these k biases. Okay. And this Dirichlet distribution is defined as, so probability of your mu is given as gamma of some alpha 0 by gamma of alpha 1, so on till gamma of alpha k times pi mu to the power alpha I minus 1. I goes from 1 to k. Okay. So here again your so alpha 0 is given by summation of all alpha i's. You have k hyperparameters now. So in Bernoulli case, you had 2 hyperparameters. Here you will have k hyperparameters, and this is the form of the distribution. So you can see that again the distribution form is exactly matching your likelihood form. Okay. And similarly, like when you will do the estimate, I didn't check that, but so please check this. I didn't check this, but I'm guessing it will be something like summation xk plus alpha k minus 1 divided by n minus summation xk. Oh, sorry, I don't need to do this. N plus summation alpha I goes from 1 to capital K minus k. This will be the form. So it's again a very simple generalization of your Bernoulli random. Okay. So we are almost out of time. So let me just finally introduce our favorite Gaussian distribution. I don't think it needs any introduction, but so this is clear again. So basically, so far, like on very high level, for Bernoulli random variables, we have very good conjugate prior called beta distribution. Similarly, and you can generalize these Bernoulli random variables to multinomial distributions, which are essentially distributions over these positive vectors, positive sparse vectors. Here you can see that this is a sparse vector and it is positive. Extremely useful for modeling text data. And here again you can, a very good prior that you can define is something called Dirichlet distribution or Dirichlet prior. Okay. And later on, like when we'll study these LDA methods and all, there you will see the power of these distributions and how they are used to model text data. Okay. So one final thing, which is Gaussian distribution. So this is like, so far all the examples that we considered, they were sort of continuous distribution. This is, sorry, discrete distributions. This is first continuous distribution that we are looking at. So probability density function of some x given your mean and variance, or sorry, standard deviation, is given by 1 by root 2 pi sigma e to power minus x minus mu square by sigma square. And similarly, if you want x to be a vector, then your mu will be a vector and the sigma will be now be a matrix. Okay. So if you have a Gaussian distribution over d dimensions, then this is the form. Okay. And as I said, that sigma is now a d by d matrix if you have d dimensional Gaussian. This is the determinant of sigma. Sigma should be a positive definite matrix. If you don't know what does positive definite mean, we'll discuss that in next class. Okay, and intuitively, basically, what this sigma does is it sort of skews your distribution or correlates your distribution in some particular directions. That is, if you, let's say you are working with two-dimensional Gaussian, and if you sample points from this, they will look something like this, like there will be a spherical symmetry. But if your sigma is skewed, that is, if some of your variables are correlated, then if you sample your data points, the data points will look something like this. You will not have many points here or here. Okay. So again, I mean, some very simple things, like if you do your maximum likelihood estimate of your Gaussian, you will have summation xi by n. If you do, and you will have to do your estimate of sigma also. So maximum likelihood estimate of your parameter sigma is given by summation xi transpose by n. Okay. So these are just maximum likelihood estimates. Similarly, you can define map estimates based on one very popular conjugate prior called gamma distribution. So that distribution is little bit more clumsy and hard to explain, but you can like look in book, and similarly you will get very similar forms for your map estimates also. Okay. So any questions or comments? Yeah, we are almost out of time, so. How many people will attend next class? Okay, so one guy. So I guess like very like high order bits are that in machine learning, like, you know, when you observe data, you can do two types of estimates for your parameters or your beliefs. So for example, I'm believing that my distribution is Gaussian, and that's why to, you know, exactly specify my distribution, I'll need two type of parameters, my mean and covariance. All right. Similarly, in Bernoulli random variables, I just need to specify the parameter mu, which is essentially just the mean. Similarly, in multinomial distributions, I'll need k parameters, mu1 to mu k. Okay. And now the question is, how do you estimate those parameters? So you observe a small number of samples from your distribution, and you can set up your maximum likelihood estimate problem or your map estimation problem. Maximum likelihood estimation problems typically are much simpler. You'll get some simpler solution. If you set up some weird bad map solution, like, you know, estimation problem using some priors, you will be in trouble. But if you use these nice conjugate priors, then you can do your map estimation also almost as easily your maximum likelihood estimate. And nice thing about your map estimate will be that if your number of samples is very small, then then your solution will be much more robust than maximum likelihood estimate. And actually, yeah, I forgot about that. So again, sorry. One last thing. So we'll have to go a little bit back to binomial distribution. So in binomial distribution, your maximum likelihood estimate was essentially summation xi by n, right? Whereas your map solution was summation xi plus e minus 1 by n plus e plus b minus 2. So here you can observe that if your n tends to infinity, then effect of these two things will go away, right? If you divide by n, so this will be 1 and then divided by n, and now take your n to be infinity, that is you have many samples, then the effect of your prior will disappear, and basically in the limit n tends to infinity, your map solution will be equal to your maximum likelihood estimate. And this you will see again and again in several learning algorithms. That is, as n tends to infinity, you want your map solution to approach, or map solution to approach your maximum likelihood estimate, or maximum likelihood solution. This is also called consistency condition. That is, when the parameters goes to infinity, your map solution should be consistent with your maximum likelihood estimate. Okay. All right. So hopefully I'll see you on Thursday. We'll do some linear algebra basics that day.